All right, hello again. So we've come to the last topic in Unit 1. If you work in semiconductor technology, you're going to hear frequently this term compact models, especially if you're working with circuit designers. So we should understand just a little bit about what this term means and how compact models are used. We will say a little bit more about compact models at the end of the course, but here I just want to introduce and explain what we mean by a compact model and what it's all about. Now, this term compact model is used in many different fields of science and engineering. It generally refers to an analytically simple model that describes some device or some phenomenon, as opposed to a fully numerical, detailed simulation where you put everything in that you can think of. So a compact model is an analytically compact description of a device, usually a solution of a set of simple equations. Now, in electronics, compact model usually means something more specific. When people say compact model in electronics, they're usually meaning a simple analytical description of a transistor, but also an analytical, simple description that is suitable for use in a numerical circuit simulation program, like SPICE or some equivalent to that. So we want to be a little careful and just differentiate between these two different uses of the term compact model. We're going to distinguish between two different types. One is a compact physical model. That's what this course is all about. A simple physical way to understand the essential physics of a MOSFET in terms of a few simple equations. We're not necessarily going to be able to use this model for circuit analysis. It could be the core of one, but it's primarily one that is used for understanding. It might be used in a manufacturing line to extract some key metrics and to fit data to the model and monitor a manufacturing line. So our focus in this course will be on this type of model. But there are also these compact models for circuit simulation. So these models accurately describe the IV characteristics of transistors, but they do so in a form that is suitable for use in these numerical simulation programs. Very frequently, and usually it's very desirable, that the core part of this model be a very physical compact model, and then a lot of complexities just to deal with real-world issues are added to that simple core model. Okay. So these kinds of models play a very critical role in connecting semiconductor manufacturing and research and development to the actual product design and the design of circuits and systems. All right, our focus is on the first type of compact models. You're trying to use them to provide insight into the operation of transistors, but everyone who's involved in electronics should know something about the second type of compact model, because this is the way we interact with designers. So this lecture is just about a few key considerations for compact circuit models, and as I said, we'll say a little bit about it here so that you know what it's all about, and then we'll revisit it later on when we're wrapping up the course. So let's begin with a very simple circuit to analyze. Power supply, a couple of resistors, and a diode, a nonlinear electronic device. Okay. Now, there's only really one node to worry about in analyzing this, and I can add up all the currents coming into that node and apply Kirchhoff's current law. So if the voltage at that node is V1, then the current through the resistor R1 is just the power supply voltage here minus V1 divided by R1. The current through R2 is, well, the voltage across R2 is just V1. And then I have the current through the diode, which is a function of the voltage across the diode. So I add those three together, they should sum to 0. That's Kirchhoff's current law. So if I do that, I have a function. I have to select the voltage V1 that satisfies this function and makes it add up to 0. Then I've satisfied Kirchhoff's current law at this node. Okay. Well, to do that, I need to specify how the diode current depends on the voltage across the diode. The diode is a semiconductor device. I need a compact model for the diode. Right? So here's an IV characteristic for a diode. Very asymmetric. The current increases exponentially in the forward direction. It saturates at a very small value in the reverse direction. It's described by a very simple equation called the ideal diode equation. There's a term here called the saturation current density, and you can see that it's related to some very physical parameters like the area of the diode, the doping density on the two sides, the minority carrier lifetime. So this is a physics-based compact model. In practice, there would be lots of complicating effects, and the models we would use, even for a device as simple as a diode, would be considerably more complicated than this one. Okay, now we have this equation. The currents coming into the nodes all have to sum to 0, and we now have a compact analytical expression for that diode, a compact model that allows us to do circuit analysis. So this is an equation that we would have to solve, and this equation is a little bit complicated. It's a nonlinear equation. It's not so easy to solve. There's no analytical solution to this equation. If we didn't have the diode, we could plot this equation, and it would just be this dashed straight line here. Because we do have the diode, as soon as the voltage increases large enough and the current through the diode becomes big enough, then the characteristic starts to deviate from this dashed line in a nonlinear way. What we're looking for is where this Kirchhoff's current law expression is satisfied, where this function is 0. That's the solution. We want to identify the voltage at which that occurs, and then we've analyzed the circuit. Okay, so how do we do that? So people typically solve this, and this is the technique that's used in most numerical circuit simulation programs. We use a method called Newton's method that you may have seen in a beginning calculus course. So what we do is, first of all, we guess. We just take a guess for the voltage. Okay, and the superscript 1 here indicates that this is our first guess. Okay, now if we plug this guess into our equation, Kirchhoff's current law, it's not likely that we're going to get 0 because we haven't guessed the correct solution. So what we would like to do then is to compute a correction to our guess that will satisfy this equation. That correction is this little delta V. Well, how do we do that? Well, if we've made a good guess, we might be close to the solution. So maybe we can expand this function here in a Taylor series expansion. So we'll evaluate that function at the current guess, and then we'll take the derivative of that function and evaluate the derivative at the current guess, and then that's times a delta V. And we'll throw away all of the higher order terms and assume that this is a good enough approximation. Okay? We want that to be equal to 0 because we want to satisfy this simplified version of Kirchhoff's current law. If we do that, we can simply solve for how much we have to correct our guess in order to get to the solution. Okay? We can evaluate a better guess. We now have an improved guess, V2. It's the first guess plus the correction to the first guess. We can plug that in the equation and see if we now satisfy the equation. We'll find out that we probably still don't quite satisfy the equation because we threw away all of these higher order terms in the Taylor series expansion, so there was an approximation there. So what do? Well, we iterate. We now have a better guess. We'll go back and repeat the process, correct it, and try to get an even better guess. And we'll just continue until we're close enough. So here is a graphical representation for how this Newton's method works. We have this nonlinear function. We're trying to find its solution. We make a guess as to what voltage satisfies that equation, but that voltage doesn't make the function 0. So we're up here. We're not at the solution. When we do the Taylor series expansion and only keep the first term, what we're doing is fitting a straight line to the function at that point, extrapolating to 0, and saying we now have a new guess. We're going to guess the voltage V1 second guess. Okay, but that's not quite right because this linear approximation wasn't good enough. We can now evaluate the function at this new guess. We've overshot the solution. We'll again go through the process. We'll do a Taylor series expansion. We'll fit a straight line there, and we'll extrapolate back. And in this case, we would almost nail the solution in only 2 iterations. So that's how the process works. We just keep iterating and we get closer and closer. And when we're close enough, in this case, the third guess is close enough, we say we're done. We've solved the system of equations. Okay, so just to review the methods for Newton's method, we have a nonlinear equation. In a complicated circuit, we have to generalize this method. We'd have a system of nonlinear equations, but the same ideas apply. We make a guess, we'll call it the kth guess. We compute a correction to the kth guess. We have an improved guess for the solution. We check to see whether we're close enough to satisfying the circuit equations. If we aren't, we just continue until we reach a predetermined tolerance. All right, so it all looks very good. What could possibly go wrong? Well, it turns out a lot of things could go wrong. So for example, what if my first guess wasn't very good? What if I was a long ways away from the solution? You can see that when I do my Taylor series expansion and extrapolate to a better guess, I've way overshot. I have a voltage that is very large, way too large. Now, when I evaluate this function is increasing exponentially because the diode characteristic is exponential. There is a good chance that this might overflow the word in the computer, and the computer might crash and stop. I won't be able to find my solution. So these are things that we have to be careful about. One of the points here is that during this process, the internal voltages will bounce around to ranges that won't occur in practice in the actual circuit, but in homing in on a solution, they might occur during the numerical solution in the computer. So we have to make sure that the function is well behaved even outside the normal range of operation of the device. We have to make sure that numbers that are too large or too small for the computer to represent don't occur and stop the convergence process. Now, there's also something we might decide, well, let's do something simpler. Let's get rid of this exponential, which causes some numerical challenges. Let's replace this characteristic by a piecewise linear model, just two straight lines. This would be much simpler. If we were to do this carefully, we might be able to get reasonable results. So instead of having this nonlinear function, we'll have a piecewise linear function. This could work if we do it carefully, but depending on the quality of the fit, we'll get good solutions or poor solutions. But there's also a very big problem here. This piecewise linear function does not have continuous derivatives. In the iteration process, when I'm solving this equation by Newton's method, I have to take derivatives. If I get close to this point, I'm going to have trouble taking the derivatives because it's not well defined at that point. And that could cause major problems in the solution of these equations by Newton's method. So, some of the requirements of a compact model for circuit analysis are that we must accurately describe the performance of the device, not just under DC conditions, but under AC small signal conditions, transient conditions. We must include noise analysis and lots of factors that are important in real circuits. We must do this over a wide range of bias and temperatures, over the range of bias and temperatures that the designer might be interested in, but over an even wider range because the Newton iteration process might encounter those biases while it's homing in on the solution. We must describe a transistor of any size because designers use different size transistors in the circuit, and it must be computationally efficient and robust so that it can be used efficiently and robustly in numerical circuit simulation programs. Now, I mentioned earlier that there are these physics-type compact models. Generally, we would like a compact model used for circuit design to be physics-based. One of the reasons for that is it relates the needs of designers to the manufacturing process. So for things like the gate oxide thickness or the doping density. Generally, it results in models that have the fewest number of fitting parameters. So it isn't simply curve fitting, it's fitting some equations that have strong physical significance, so we can usually get by with fewer numbers of fitting parameters. So it simplifies the calibration of a model to a particular manufacturing process. These models are also best for statistical and predictive modeling. If my manufacturing process has some fluctuation in gate oxide thickness, then I can use my model to assess what are the impacts of those fluctuations on the performance of the circuits that we produce. And but it isn't enough. We would like the model to have a strong physical core, but if we're using it for circuit simulation and circuit design, we also have some mathematical requirements. So some of those mathematical requirements are that in order for the Newton or Newton-Raphson process for systems of equations, in order for that process to work, we have to have continuous derivatives. Now, in order to extract small signal parameters, we also have to have continuous first derivatives. And in order to extract some other parameters that are important, especially for analog design, we need even higher order derivatives that are continuous. So generally, people who are developing robust models for circuit simulations will look for formulations that are continuously differentiable to all orders. The model has to be well behaved outside the normal operating range so that the Newton solution process will home in on the correct solution eventually. And the model shouldn't be unnecessarily complex. The simpler it is, the quicker and faster it will be able to do the analysis, which will often consist of tens or hundreds or thousands of transistors. So let's summarize. We've discussed compact models. We've discussed two kinds of compact models. The first kind is used to describe the physics, the essential physics of a device. Its primary role is insight and understanding. It might also be used to monitor a process line, keep track of some key metrics, and it could be useful in that role too. The second type of model is a compact model used by circuit designers to design electronic circuits, sometimes quite complicated circuits. So these are models, these perform the communication link between the manufacturing process and the design process. The core of this second type of model, the one used for circuit design, we generally like this to be a strongly physics-based model. But the compact model for circuit design also must satisfy certain mathematical constraints in order that it behave well in numerical simulation programs. So we'll be talking more about compact models later. This is just kind of an introduction to the terminology. We've covered a lot of ground in Unit 1. In the next lecture, I'll just recap what the important points are that you should take away from the first unit before we proceed on to the subsequent units and dive into the physics of MOSFETs.